All right, welcome everybody to the second part of chapter 7. And we're going to go ahead and start from the board. If I can get over to here. Okay. So the first thing that we're going to talk about, since we understand how series parallel circuits work now, is we're going to look at something called the Wheatstone Bridge. And we will be revisiting this in multiple chapters. And I always tell students that of all the things that I learned, this is one of the only circuits that I ever actually built in real life when I was at the calibration lab, because we would have transducers and all kinds of different electronic devices that converted some physical quantity to an electrical signal. And the best way that I could power one of those with a with a certain current or whatever the power requirements were, I would do that with a Wheatstone bridge. So I had very fine control over what the current was able to do. Okay, so the generic form of a Wheatstone bridge looks like this. There's a power source. On this branch, there's two resistors. And on this branch, there's two resistors. Okay, so over here, we call this node A, and we call this node B. So the idea here is that you have these resistor values that when you connect a load across the middle here, you have a very specific current that's driving this load, okay? So that you don't have too much and you burn it up, or you have too little and it doesn't work, okay? And if you have your resistor ratios correct, then you can pretty much hook up any device that requires current, okay? So if I call this R1, R2, R3, R4. Okay, and then here is our source voltage. Okay, just want to point out a couple things about the way that this is set up right now. Okay, first thing I want to point out is that this right here, all of that is one single node. Okay, down here, that is all one single node. So across from here to here, that's the total voltage drop, right? Because this positive terminal is connected here, it drops the whole voltage of the source on this branch, and it drops the whole voltage of the source on this branch, okay? So as far as the Chapter 7 analysis of these Wheatstone bridges, it's pretty straightforward. There's not a whole lot of extra work because once you load, once you put a load in the middle here across A and B, now you can no longer use Chapter 7 techniques. You have to go to Chapter 8 and Chapter 9. Okay? So all we're going to focus on here in Chapter 7 is finding out what this node voltage is and finding out what this node voltage is. Okay? That's as far as we're going to take it. And then when we actually load it, we will revisit the Wheatstone bridge and use some other methods to solve a loaded Wheatstone bridge. Okay? So in terms of what the A and B voltages are, sometimes a device requires a certain amount of voltage and it has a certain amount of current that it has to have driving it. And so we're going to find out what these two node voltages are and what the difference is between them. Okay, and so just for reference, when I do this work, when I talk about VA, right, that's a node voltage, right? V sub S, that's the source voltage. But when I'm talking about a node voltage, I will do V sub A, V sub B. Anytime you see this notation, I mean that this is referenced to ground, okay? Whereas, if I was talking about across a resistor, like VR1, now I'm talking about the voltage potential from here in reference to the other side of the component. But when I say just the single letter here like this, and I note that this is where my node is, what I mean by that is what is the voltage at A with respect to ground or zero. Okay, so there is no subtraction there. It's just whatever this voltage is the node voltage reference to ground or zero. Okay. All right, so essentially it's just going to be two voltage dividers on each side. So the voltage part of this is pretty straightforward. So let's go ahead and do that. I'm going to go ahead and create one with a few values in here. And let's use a 9-volt source. And over here we've got 2.2K, 3.3K. There's my node A. And over on this branch, I've got a 1K and a 3K. Right? Now, if you wanted to see, if this was a balanced bridge, I would say a balanced bridge exists when the ratio of, if we stick with our notation here, R1, R2, R3, R4. Okay? So when the ratio of R1 to R2 is equal to the ratio of R3 to R4. So in other words, if I would have had 2.2K and 3.3K, and then over here I had 220 ohms and 330 ohms, even though they're, this one is multiplied by, take that value, multiply by 10, okay, those still have the same ratio. So what you would end up with is VA is going to equal VB, and when you take the difference between the two, you get 0 volts, right? So if you load this up and this node voltage is 17, or let's say it's 7 volts, and this node voltage is 7 volts, then you're not going to have a voltage drop across your device, okay? So here we go. So a balanced bridge exists when the ratio of this resistor to this resistor is the same as this resistor to this resistor, okay? So let's go ahead and find node voltage A. There's a couple of different ways that you can approach this. One way would be to, look at the whole thing and say there's 5.5K ohms of resistance on this branch. And I know it drops 9 volts, and then do the voltage division for each one, okay? So I'm actually going to just do the voltage division to find this voltage, because I don't really care what that voltage drop is up there. This voltage drop down here, because this is connected to the negative terminal of the battery, this is essentially ground, right? Or my 0 volts. So if I just take the voltage from here to here, I'm grabbing the node voltage. So in this case, and in all Wheatstone bridges, VA equals whatever the voltage is across R2. And for all of the examples that we do, VB equals the voltage of the resistor R4, if we stay with this naming structure here, okay? So all I have to do is find the branch voltage for this resistor, and I'll have VA and VB, and then I can find out what the difference between the two is. Okay. So the voltage at A, there's a 9-volt drop total. So now this is going to be times, remember in the voltage division, it's the individual resistor over the total, which is 5.5. And for VB, the way we set it up would be VB equals 9 volts times 3K over the total of 4K. So essentially 75% of 9 volts, right? Let me go ahead and punch these into the calculator and get some answers. So 9 times 3.3 divided by 5.5, I get 5.4 volts. And for the bottom one, if I take the 3 divided by the 4, I get 6.75. Okay? So that means that my node voltage at point A is, what do we say, 5.4 volts. Okay? The node voltage at B here is 6.75 volts. And that means that we have an open circuit voltage, which I will also write as VAB. So the O.C, where O.C is open circuit. Okay? So open circuit voltage is the same thing as VAB. Now when you have two node voltages together like this, what that means is you take the first one minus the second one. Now in this case, that's going to give us a negative value. So it's really the absolute value, okay? I don't want a negative value from you when you do this, okay? So I'm just going to do 6.75 volts minus 5.4 volts. And what is that? 1.35. So the open circuit voltage there for this Wheatstone bridge is 1.35 volts. Okay? And as far as chapter 7 goes, that's as far as we're going to take this. Okay? We're not going to worry about finding any currents. We're not going to worry about finding any, I guess we could find the current on each branch right now, but we're not going to do that. We're just going to worry about finding the open circuit voltage, because when we load this, we're then going to use mesh and nodal, or maybe even Thevenin or Norton's to fix this, okay, or to solve this. Okay, so there's the first one. Now let me show you what I mean by a balanced bridge. And I'll just get rid of this and this and change the values up. So how about 4.7K and a 5.6K and a 470 ohm and a 560 ohm? Okay, so different values this time. So let's go ahead and find VA. It's going to be 9 volts times, in this case, 5.6 divided by, so what is that, 10.3, okay? And VB will be 9 volts times 560 over, I guess that's just going to be 1,003, right? So 1.03K. So let's see what we find here. So 9 times 5.6 divided by 10.3, and I get 4.89 volts. And for VB here, I change that to 0.56 divided by 1.03, and I get 4.89, which I expect. Okay, so I have, my VAB is 0 volts, because this minus this gives me 0. Okay, so this is what I would call a balanced bridge, where you have a voltage drop here. The currents may be different, but you're not going to have any voltage drop across the middle load, because this thing is balanced right now. Okay, all right. Now let's take a look at another type. Again, I'm just using chapter 7 techniques, which are built on KCL, KVL, and Ohm's law. Okay. Now an R2R ladder network is used in digital to analog conversion all the time, and I'll show you why. Okay. Here's the generic format for an R2R ladder circuit. Okay, so there's R, this is 2 times R. This is R, this is 2 times R. And then finally over here, 2 times R. And then this is our source. Okay, so we can keep taking this ladder out as far as we need, right? I only have a few of these here. But anyway, whatever this resistor value is, let's call it 1K. This one is 2K. This one is 1K. And then finally you end this with 2 R's in parallel. Okay, so what happens here is if you look at how this reduces down, because this is again a chapter 7 technique, so I can find the total resistance here. If I just look over here, 2R and 2R in parallel gives me R. If I replace that with an R plus R is 2R. That means 2R in parallel with 2R is R. And then I finally have R plus R. So the total resistance in a ladder network is always 2 times R. Always. Doesn't matter if this is 1K and 2K or 50K and 100K. All right? The total resistance is always going to be 2 times R. So that makes this analysis very, very simple, because then you can jump right to the IT and say VS over RT to find the total current. Okay? And then you just have to see how it splits up throughout the circuit. Okay, now I just dropped my microphone, and as soon as I pick it back up, I will tell you that you don't even need to go that far with R2R ladder networks because of the symmetry that's going on here. So let me work an example and show you what I mean. I'm going to work this as if I don't know how R2R ladder networks work, and I'm going to approach it as a Chapter 7 technique problem. And I'm just going to use 5K and 10K ohm resistors here. And I'm going to give myself 10 volts this time. All right, so this is a 5K. This is a 10K. And instead of just doing one single 10K on this outer branch, I'm going to do, no, I'll do it this way first. Okay, just put another 10K out here. All right, so what I was about to do was have two resistors on this final branch, and one of them be 5K and another one be another 5K, but I'll show you why I would do that later. Anyway, here's an R2R ladder network. I don't know that that's what it is, so I'm just going to solve it like we would if this were the part 1 video. So I'm just going to look at these two over here, and so if I redraw this, okay, my REQ of 10K in parallel with 10K is 5K. So let me redraw this. There's the 5K. Here is the replaced 5K, just to point this out. Okay, I replaced those two branches with this one single. So now on this branch I have 10K in parallel with this 10K. So again, REQ is going to be 5K because here I've got 10K in parallel with 10K. All right. So if this one I mark with red and I redraw this again, here's my 5K, 5K, and now my total is 10K. Okay, so I'm not going to do that again. For all future R2R ladder networks, I'm just going to go with putting 2R as my total resistance. Okay. So if my total resistance is 10K, my current is 10 volts divided by 10K, which gives me 1 milliamp. So that's my total current right now. 1 milliamp. Okay. Now, if you remember from this one, I shouldn't have erased it, but so 10 volts, 5K, 10K, and then this was 5K and 5K, right? If I keep this stuff separate. Okay, so this is what we had before, and so that 1 milliamp is going to come into this node and split between here and here. Now notice, this is 10K and this is 10K. So they get exactly the same current. They're just going to take that 1 milliamp and split it. So this is 500 micro, and this one is 500 micro. Okay, now let's look what happened in the, gosh, if we replace this one, right? So 5K, 10K, we already know what these currents are. Now we've got the 10K and 10K out here. So we know that this from above here is 1 milliamp. This one is 500 micro amps. This one is 500 microamps, right? But now this thing right here, right? That comes from two 10K ohm resistors in parallel. All right? So again, they're the same value, so this is going to split right in half again. So this is now 250 micro, and this is 250 micro. Okay? So I can easily predict all of these currents because I just take whatever the total is and halve it each time. And when I say halve it, H-A-L-V-E, halve it, half it. So this is 500 milli. That's 500 milli. it gets split 250 micro. I'm sorry, not milli. That is micro. 250 microamps. 250 microamps. Okay. So when you do these problems, I mean, this is the amount of work that I expect right here. Right? I don't expect you to go much further than this, because once you have your total, just divide it by 2 and then divide that one by 2 and divide that one by 2 for as many branches as you have. Okay? So as I always say, once you know all of the currents, then you can find all of the voltages. So let's just find a few of these. Let's find this 10K ohm. So we're talking about this right here. Okay? So I want to do this in black. So the voltage of the 10K that we're pointing to is 500 microamps times 10 kiloohms. If you do this in your calculator, you will get 5 volts. So that's essentially my node voltage right here is 5 volts, right? Because 500 microamps times 10K is a 5 volt drop. Now let's do this one. Okay, so now I'm pointing at this one for the voltage on that 10K. And that one is 250 microamps times 10K. And what you'll find here is 2.5 volts. So once again, we have halved the node voltage. Okay. So now this should paint the picture of what you should expect for all R2R ladder networks. Whatever the source voltage is, every node along here in the network is half of what the previous one was. 10, 5, 2.5. So once you have the total current, again, you split that. 1 milliamp, 500 micro, 250 micro. Okay? And this just keeps going out as far as you need it to go. Okay, so I want to do one now with a little variability. I still want to make it easy enough to do in my head. So let's go with 20 volts. And let's see here. How about 20K and 40K and 20K and 40K. And now this time, I'm going to do the split that I talked about. I'm going to do 20K and 20K. So why would you do that? Well, for one thing, it gives you an extra, right here, it gives you an extra node. So I already know that this one's going to be 10 volts. I already know that this one's going to be 5 volts. And this one is going to be 2.5. Okay, so if I need those node voltages, I have them available. Okay, so really I just need to, I know what the total current is, or I'm sorry, the total resistance. It's going to be 40K. So that means my total current is 20 volts divided by 40 kilo ohms, not amps. And I should have 500 microamps. Okay, so that's my total current, 500 microamps. This one is 250 micro. This one is 250 micro. This one is 125 micro because that's half of 250. And this entire branch is 125 micro. Okay. So there we go. I just analyzed the whole circuit, and all I had to do was one single calculation if you don't count, dividing by 2 up here. All right. And so then the final thing that I want to show, let's see. Final thing I want to show here is meter loading. Or you could call it distorting measurements. Okay? So, when you're in voltmeter mode, and here's my DMM. And here is my volt, and then here's my common. Okay, so if I have another meter, so here's my ohm meter, okay, and I have my black lead and my, I guess I could use my colors here, and I had my red lead, and I took this meter and I measured the terminals while this one is in voltmeter mode. Okay, so you're actually physically measuring with another meter the resistance across those two terminals. What you'll find is that it should be very high. And when I say very high, 10 mega ohm, 1 mega ohm, 100 mega ohm, something very, very big. Okay, if you were to measure those two terminals. If, however, you had it in voltmeter mode, I'm sorry, if you had an ammeter, so this is now an ammeter mode, and we know that the ammeter plug is over here. We can go from here now to the amp side. Okay, get rid of this. So, if while this thing is in ammeter mode, we measured those terminals, these should be very low. And when I say low, less than 10 ohms. Okay, so in voltmeter mode, it's a very, very high resistance, and in ammeter mode, it's a very, very low resistance. Okay, and here's why that is. Let me just bring up a simple series circuit. Okay, to illustrate this, just a 2 resistor series circuit. Okay, and this one is a 2.2K, this one is a 1.8K, and then we have, let's see here, we have a 10 volt source. Why not? Okay, so here's what we should expect. If I wanted to know what the voltage on the 2.2K was, right, I'd take 10 volts times 2.2K over, what is that, 4? So 10 times 2.2K divided by 4K, and I get 5.5 volts. Okay, so that means that this one would be 5.5 volts. This one would be the other 4.5 volts. Okay, and that's to be expected because this one's a little bit bigger than this one. Okay, that's what I should expect. So let's say that I now have a very high resistance, and instead of K's, I use 1.8 meg, and this one is 2.2 meg. Okay, so 1,000 times larger in each case. Okay, so now this time, I should expect to say, I'm using the same ratio, right? I just multiplied each by 1,000. So I should expect that the voltage on the 2.2 is still going to be 5.5 volts, right? Because it's all about the ratio. And the voltage on the 1.8, I should expect 4.5 volts from our discussion just a second ago. So if I go put my meter on here, and I want to measure the voltage, and let's say that the resistance measurement of my voltmeter on my DMM, let's say that it's 1 meg. Okay, maybe this one's a little bit cheaper, and they don't have as much protection on the terminals. Okay, so let's say that that resistance right here is 1 meg. What I've just done is create this circuit, and this happens every time you make a voltage measurement, by the way. It's not just this example. Every time you put those probes across a resistor, you've just put that meter in parallel with it. So if I do have a cheaper meter, okay, now what I have out here is essentially a 1 mega ohm resistor. This is how I have to look at that circuit when I analyze it, because that's what I've just done is put this 1 mega ohm resistor out in parallel. So, you know, if I ask you the question, what would the voltage be on each resistor if the meter was not distorting the measurement? And then I would ask you, what would be the measurement if the meter was distorting the measurement? Okay, and so that's in this high resistance category here. So I'm actually, to give myself some space, I'm just going to rewrite this up here as a big resistor, big orange resistor. And that's 1 meg. Okay, so now my total resistance is no longer just adding those two together. Now it's 1.8 meg plus these two in parallel. So let me find out what that calculation is. So I have 1 divided by 2.2 plus 1 divided by 1. Take that thing to the negative 1. 688 ohms. So that REQ, I'm going to write it up here, is 688. Which means that the total resistance here is that number plus 1.8 gives me 2.49. Well, that's not right. Yeah, that's right. 2.49, because take this plus this. Okay, so that's my total resistance. So now my total current is going to be 10 volts divided by 2.49 meg. And I get 4.02 microamps. So I've got 402 microamps coming in here. And so now I got to split that apart, and we'll see what's across this resistance here. Did I put it up there? 4.02. That would help. Okay, so if I want to know the current through the 2.2 meg, that's going to be 4.02 microamps times, we said that the combination there is 688 over 2.2 meg. So 4.02 times 6.688 divided by 2.2, I get 1.23 microamps. Okay? So if we want to now know the voltage on the 2.2 meg, we take the 1.23 microamps times 2.2 meg. And I get 2.71 volts. Okay? That is not 5.5 volts. Okay, so we have a very, very low voltage drop here. And so that's going to be the current through the 1 meg, and that equals 4.02 micro times 688 over 2.2 meg. Whoops, that was not correct. So 4.02 times 0.688 times 2.2, and I get 6.08. Oops, I took it times, didn't I? It should be divided by, and it should be divided by 1. There we go, 2.77. Okay. All right, and that's going to give us the current because this is a 1 meg, and so yeah, 2.77. That's not volts. That's microamps. 2.77 microamps, and so we have a 2.7 volt drop across 2.2 meg, and we would expect that the 1 meg would have the same voltage drop. So the voltage of the 1 meg equals 2.77 micro times 1 meg, and you can guess 2.77 volts. I got ahead of myself here. Okay? So that's how it distorts. So if the circuit is a high resistance circuit, then the voltmeter can distort the measurement, and you have to be careful of that, okay? Now let's come in here. And we'll do another one. Same thing, just 2 resistor series circuit. 1, 2. And we'll make these easy. How about 10 ohms and 20 ohms. And let's make this a 30 volt, just to make the math easy. 30 volt source, okay? So what I expect for a voltage drop here is that I'm going to have, well, let's find the current, okay? So the current is going to be 30 volts divided by 30 ohms. And so I expect 1 amp, okay? Now, if you were to put, this is why also it's so dangerous to have an ammeter. If you were to put an ammeter in parallel, right? Essentially what you're doing is you're putting like maybe a little 5 ohm down here. And so it's going to bypass that and come over here to this side. But anyway, we're not going to look at the voltmeter this time, but we're going to use the ammeter properly. And let's just go ahead and stick it right here. So there's my ammeter. So in theory, on paper, my ammeter will measure that 1 amp. Okay? Now, as we said before, let's say that this one, the resistance of the ammeter on my DMM, let's call that 7 ohms. Okay? So now that changes the dynamic of this circuit. Because now this is essentially a resistor up here of 7 ohms because I put it in series with the rest of this because that's how we use an ammeter, right? Now my total resistance is 37 ohms. And so now my current is going to measure 30 volts divided by 37 ohms, and I'm going to wonder what in the heck happened to the rest of that current. So 30 divided by 37 gives me 810 milli. So that's almost a 20% loss in this very low resistance circuit. So that's what will happen if you have a very, very low resistance circuit. So in both cases here, if you have a very, very high resistance circuit, then you have to be careful about your voltmeter. You have to know what is across the terminals. And in Multisim, you can actually change that. And I'm going to go ahead and go into Multisim here in a second and show you how that works. If you have a circuit with a very, very low resistance, total resistance, then you are going to distort the measurement if you make an ammeter measurement. Okay? So in both cases, we have to figure out if our circuit is being affected by the meter loading and see if there's any distortion. Because sometimes that can account for a bad measurement. Okay, so let's go ahead and look at Multisim with a very similar setup to what we just did. And here I've just got a 5K ohm and a 10K ohm resistor in series, and when we make this measurement, I haven't changed anything yet. It goes ahead and spits out whatever the voltage is supposed to be, right? These are very low. They're moderate resistance values, and so I'm not in any danger of this distorting the measurement, okay? Now, if I measure my device and I actually want to put that number into Multisim to have it do a real-world simulation, I can go right here to this button that's called Set, and I can plug in what the actual resistance is. Now, they are assuming a super-duper voltmeter resistance here of 1 giga-ohm. I'm going to change that and just make it 1 meg. Okay, and I'm also going to change this to a 10 meg and change this to a 5 meg. Okay, so I forget what it was before, like 6.88 volts, somewhere around there. Let's see what happens now that I've changed and made this more like a real-world multimeter. Now it's just measuring 1.538 volts. Okay. So you would say to yourself, ooh, there's a problem here, but it's because of your meter, right? Even if I make this 10, it's still going to distort the measurement. Okay? It's saying half and half here because that would be 10 in parallel with 10, which would be a 5. Okay? Now, if I get rid of this and I use it as an ammeter, And let me go ahead and throw it in here. Let's see what the baseline measurement should be with a near perfect or theoretical device. So I have this now in ammeter mode. I'm not going to change anything, and I'm going to run it. Okay, so these are very, very high values. I don't want those high. I just want to do an example here. 5K, and then let's make this one 10K. Now we run it. And okay, so 667 microamps. Okay, now let me come in here and I measure mine, and let's see here. Let's make this 5 ohms, just regular 5, and let's just make this 10. So similar to what we did up here. All right, and so now I'm going to set this. Oh, look at that. They have the super duper ammeter that's only 10 micro ohms. So let's go and let's make this. I said 7 in my example, so let's call it 7. Okay, now let's see what happens when we do the measurement. It's a lot worse, right? It was 667, and so now we've got 454, right? So if I come back in here and set this to micro ohms again, it won't distort the measurement, and so this is what we should be getting, which is that 667 milli. And when I set it to what what my thing actually is, if I said it was well, that's voltmeter. I said this was 7 ohms. You can see how much it eats up. Okay, because there's a voltage drop there now because you have such low resistance in total that this is now going to drop some of that voltage. It's almost like a component. That's why you can do the circuit analysis by looking at this as if it were a resistor. Okay? All right, I think that concludes the second part of this Chapter 7 discussion. Thanks for watching.